We're going to discuss how to use nodes in order to distinguish the arrangement of the resistors in series or in parallel. As a review, I would like to go back to the simple representation of the circuit where the power supply here is providing the electromotive force. It is pushing the electrons through, and the electrons are going to have to pass through this wire and the components that are connected to the wire. The electrons, when leaving the power supply, have the highest electromotive force applied to them. They have a higher potential. So point A here is the highest potential point in this circuit. The electrons are going to go from point A to point B, and they are going to see no resistance in their flow. There is nothing pushing back in their way. The electrons are going to lose minimum negligible amount of energy. So when they go from point A to point B, the electrons have not lost energy. Therefore, we say the potential of point A and the potential of point B are equal for practical purposes. In real life, you can prove that there is always a little bit of energy that is lost when the electrons are going through a piece of wire, but we completely neglect it because it is a very, very small amount. So for the practical purposes of this course, we say that potential of point A and point B are the same. The electrons then are going to pass through the resistor in this case, and they are going to lose energy because the main purpose of a resistor is to resist the flow of the electrons through it. And when they lose energy, they end up in point C at a lower potential, lower electrical potential. Therefore, we say that the potential of point A is higher than the potential of point C, and we can represent it in this way. And when there is a difference in 2 points, like a potential difference in 2 points, we say that there is a voltage drop between those 2 points, meaning that the potential, the electrical potential of point B is higher than the electrical potential of point C. Therefore, the electrons have lost some energy. In other words, there was a voltage drop. Now, when we look at C to D, we also notice that there is no resistor in there. The representation is of a wire, and wires, as we said, are elements of no resistance for practical purposes. Therefore, point C and point D will have the same potential, electrical potential, and there's no voltage drop. The same voltage drop that we talked about between B and C is going to happen between D and E because there is a resistor between D and E. The electrons are going to try to flow through, the resistor is going to resist the flow, and the electrons are going to fight back. They're going to win in this case, but they are going to end up losing energy. Now, therefore, we say that there is a voltage drop between point D and E. In the same way, if we look at the electron flow between E and F, we see that there is no resistor, there is no resistance, and therefore the electrons are not going to lose any energy. In this most simplistic way of presenting a series circuit, we're going to notice some things. First, we are going to identify these spaces where the electrons are not losing. I'm highlighting those paths or part of the paths where the electrons are not losing any energy. Those highlighted areas, each one is called a node. More practically, I should probably use different colors. So we have the first one is highlighted green, the second one is highlighted magenta, and let's highlight the third one with a blue. So these three highlighted areas of the circuit, the path of the circuit, these three are, each one is called a node. So a node is basically a single electrical point but not necessarily a single physical point. It's a single electrical point where there is no voltage drop, there is no potential difference at any point compared to any other point within that node. So theoretically, if you have a wire that is 1,000 feet long, that one wire will represent a node, a single node, because the whole wire will have a single electrical potential compared to the ground, for example. And it means that at any point on the wire, we can measure the voltage to another point on the wire, and the voltage difference is supposed to be zero. That's the definition of a node. So when in a bigger picture of things, if we look at a diagram like this, for example, we can see that this is the blue node that we were talking about, and we have another node here that the electrons start flowing. This is the start. The electrons actually leave the negative. The electrons leave the negative side of the power supply, but for the conventional flow direction of the electrons, we say they leave the positive side, which doesn't represent the reality, the physical reality as we understand it. It's just a convention that we say the current is flowing this way. In reality, the current actually flows this way. Right, so we are going to have another node here and yet another node here. So in this diagram, we have 4 different nodes. We have 1, 2, 3, and 4 nodes. So as you can see, between node 1 and 2, there is the resistor R1. Between 2 and 3, there is the resistor R3. Between 3 and 4, there is the resistor R, I should say actually, in here, it should say R2. It's a mistake. All right. So the idea of a series circuit is that the current that is flowing through one resistor in its entirety should flow in through the other resistors. So if these black arrows represent the current, if this is the current I1, which goes through resistor R1, then I2 here is supposed to be equal to I1, and I3 here is supposed to be equal to I1 and I2, which we say is equal to I total. This is the representation of a series connection. In a series connection, you have resistance, the resistor, first one, and then you have a second resistor, let's say R2. In a series circuit, the current that is passing through one should pass in its entirety through the second one, meaning that they would be connected in this way. However, in a parallel circuit, that is obviously not the case. There's supposed to be different connections there. So, for example, there is a node in this parallel circuit right here, and there is another node right here. In a circuit that is strictly parallel, meaning everything is connected in parallel, you will have only 2 nodes. This will be one node, and this would be a second node. This would be the proper representation of a series circuit where everything is connected in, parallel, where everything is connected in parallel. Now, everything in this node here is obviously going to be same voltage, and everything in this node here is going to be the same voltage. So basically, in a parallel connection, the resistors are going to share one node at one end and another node at the opposite end. That's the definition of a resistors in series. So if I have a resistor 1 and a resistor 2, what will happen is they have to share one node at one end and another node at the opposite end. That's the only way 2 resistors might be in parallel. Now, please pay attention that series and parallel is not the only 2 states in which resistors can be in relation to each other. 2 resistors can be not in series, not in parallel. You have to remember that. Now, If we look at the diagram here, we can see that these two circuits are identical. These two circuits are identical. There's the power supply, there's the power supply, there's R1, which is in parallel to the power supply. R1 is in parallel to the power supply in the second. And then there's R2 and R3, like these ones, are in parallel. So these two circuits are absolutely in parallel, in the same. They are represented in two different ways, but they are the same. As you can see, if I go back to the node analysis, this is one node, and this is another node that is connecting everything in the circuit, and everything is in parallel to everything else in this circuit. Of course, life is not that easy, but we're going to have to live with it. All right, now the switches are components that would make it easy to connect or disconnect a node or a component or any part of the circuit. In this case, for example, this circuit is identical to a circuit that looks like this. This is our load, this is E, and this is our load. Everything else, this two circuits are the same. Everything else that is represented in this circuit here is simply additional and do not necessarily make a part of this circuit, except the switch itself. Now, what you see is that the switch, when the switch is closed, what will happen is that there will be connectivity in this red node right here. And of course, this blue node is always connected. There's no switch in that blue node. So the red node, to be connected, the switch must be closed. Well, what would happen if that red node is not, or the switch is open? What will happen is the connection will be like this. That's it. The connection will stop. There is not going to be anything in here. There is no connection in here. And therefore, the switch is going to play a role in terms of connecting and disconnecting the RL. In similar kind of congruent way, we can say that the switch is here, and it is playing a role. So adding a switch will result in either making or breaking a circuit.